Today we're going to talk about different types of matter, and I have a feeling that the majority of this is going to be review for you. So I'll try to be as quick as possible. So first we're going to define matter. Matter is anything that has mass and takes up space. So mass and volume. We're going to talk about the three phases of matter that we discuss in this course. I know there's a fourth one you've probably heard before called plasma, but we're not going to deal with that in this course. So solids have a definite volume and a definite shape. The particles in a solid are in a regular geometric pattern. And there is a strong attraction between those particles. So the forces of attraction between them are relatively strong. All right. Next, liquids. Liquids have a definite volume, but their shape is variable. So they take the shape of their container. The particles are more spread apart and not as regular. And there's a moderate attraction between them. And then the last, you can guess, gases have a variable shape and volume. The particles are far apart and have very little attraction. We've discussed particle diagrams in the past, but essentially they show how the particles relate to one another. All right, so let's move this so we can show. In a solid, when you draw the particles, you're going to want to draw them very geometric, very regular, as best you can. I'm not a fantastic artist, but note that they have their own shape within the container, and they're very neatly organized. In a liquid, they're going to go all the way across the container so that you can show that they're taking the shape of the container they're in, but they're not nearly as organized as the solid. And then the gas, you're going to show them very far apart and spread through the whole space. True solids are substances that have definite melting point and a crystalline structure, so a very regular geometric pattern of the particles within it. Examples of true solids would be any salts, sugar, solid iron. Those kinds of things would be examples of true solids. There's another type of solid called an amorphous solid. Amorphous solids don't have a regular geometric pattern, and they don't have a definite melting point. we'll say a variable melting point and not as organized. These are things like plastic, wax, and depending on the preparation, glass can be an amorphous solid. Matter can be classified as a pure substance. Those are only elements and compounds. Or they can be mixtures. So they're any combination of elements, compounds, molecules, things like that. What's important is that they are not chemically combined. They're just mixed together. These mixtures come in two different ways. They can be homogeneous, which means they're same throughout. And by that I mean if I had something that was a homogeneous mixture in my beaker, wouldn't matter if I got a scoopful from here or a scoopful from down there, it would have the same amount of the different substances in there. Examples of things that are homogeneous are when you have a solid dissolved in a liquid, and for that you would see after the formula of the substance, take for example salt water, you'd see NaCl and then the AQ. So any solution would result in a homogeneous mixture. Another is if you had a gas mixed into a gas. Gases as a mixture are always homogeneous. An example of a solid and a solid that would be homogeneous would be like bronze. So alloys are homogeneous. And then liquids in a liquid whose densities aren't too different and polarities are the same would also be. So a liquid in a liquid, an example would be like ethanol in water, or isopropyl alcohol that you buy at the store is actually a solution of isopropyl alcohol in water. So again, it would probably say AQ after it to tell you. So if it's aqueous, it's always homogeneous. So if it's a gas in a gas, it's always homogeneous. And if it's an alloy, it's homogeneous. Heterogeneous mixtures are different throughout. So if we were to use the same example, if I were to have a beaker with my mixture in it, and I took a sample from here, I'd have a different ratio of the substances in it versus from down here. Examples, if I had two solids like iron and sulfur mixed together, they would not be homogeneous because it's not like I melted them together. Sulfur wouldn't mix homogeneously with iron. Another one, when you put something in water that does not dissolve, like take for example if I put sand in water. We appreciate that the two do not actually mix properly, homogeneously, because otherwise all of our beaches would dissolve away. Another thing, milk. I know it says it's homogenized, but it's actually a colloidal suspension of the fat in the milk, so it's not technically homogeneous. Another example you may have had exposure to would be concrete. Concrete has rocks and lime and all sorts of stuff mixed in with it, and it's not homogeneous. And that's probably good because at the surface we want it to be nice and smooth, and if the rocks were at the surface then it wouldn't be smooth. All right, now what's important about mixtures is that sometimes we need to separate them and get out the different substances within. Because one mixture versus another is different, the composition actually varies. And therefore, the physical properties vary of that mixture. We can use physical properties in order to separate them. So some methods for separating mixtures. One would be using magnetic separation. This works if you have iron. Other metals are not attracted to a magnet like iron. So if you have iron and any nonmetals or other metals that are non-ferrous, you can separate them magnetically. Another way is by filtration. And filtration works only if you have a solid in a liquid. So if I was separating sand from water, I could use filtration. Another way is density. If the two liquids, or if there's a solid in there, we can actually use density. And you'll actually, I'll put two liquids with different densities, or a solid in a liquid. Another way you might describe this is to decant. So essentially you're pouring off a layer. So the two liquids would not be dissolved in each other. There would have to be two layers in order for this to work. Another way is particle size, and you probably did this in Regents biology with, I think you use markers, but typically we use it for chlorophyll, because there's different types of chlorophyll in plants, and you can separate the different kinds of chlorophyll this way, the different sizes of the particles. We call this chromatography. And then another way, which I'll show you in class, is distillation. Distillation is when you have two liquids dissolved in each other with different boiling points. So one will begin to boil before the other, allowing you to separate the two. All right, now drawing particle diagrams for mixtures. If we have copper and zinc and brass, this is an alloy. And if you recall, alloys need to be homogeneous. So I'm going to show my two different particles of copper and zinc, and they don't necessarily have to be equal in proportion, but they need to have the same proportion throughout. So copper I'm going to show as an open circle, and zinc I'm going to fill in my circle. And it doesn't necessarily have to be 1-to-1. You could have 1-to-3, but you're going to have to keep that ratio throughout your mixture or it won't be homogeneous. So it's a solid, so I'm going to give it its own shape, and they need to be regular geometric pattern. So I'm going to do every third as zinc. Then I'm going to repeat that pattern above. And that's proving it's a homogeneous mixture that's a solid. All right, for the next one, I'm going to show a heterogeneous mixture. So I don't want to have my pattern being regular. Plus, it's two different liquids. So I'm going to go all the way across my container with not perfectly arranged molecules that are not really touching each other and make sure that it's not heterogeneous. So I'm going to actually show it as layers because that's what I think of when I think of two liquids that are all heterogeneous. They'd be in layers like oil and water. So I'm going to show a layer of open circles that look like a liquid, like so, and then I'm going to do a layer of solid circles that are also like a liquid, like so. And that'll show that it's heterogeneous. The last one we have argon as a gas. This one isn't actually a mixture. Argon is a noble gas, so it's not going to be bonded to anything else. It's just going to be single circles. So I'm just going to kind of spread them throughout my space like so. And that's how you do the particle diagrams.